Hello everyone, reporting today for First Updates Now, I'm Abbas, and with me here today is Team 11212, the Clueless from San Diego, California. It is an absolute pleasure to interview Clueless. They just have such an amazing robot this season. There's so much to talk about. I mean, just stats-wise, they have the #1 world record at 416 points right now. They have the #1 non-penalty OPR at 192 points, and the #1 non-penalty average score. Just absolutely fantastic team, such an amazing robot, so much to talk about coming up on First Updates Now.
This video on fun is brought to you by viewers like you and also in partnership with the following. Discover how Kettering University students engineer their success with Kettering's amazing co-op employment programs where students earn great pay and gain valuable experience. Those accepted into Kettering University can apply for a robotics scholarship, providing up to an additional $5,000 a year in tuition assistance. Head on over to kettering.edu/first to learn more and apply. Support Fun's content creators when you sign up for a membership on YouTube Join. You'll get access to special perks like emotes, loyalty badges, and Fun members will even get early access to our scheduled videos and more. 100% of this revenue will go back to our correspondents to help recognize their efforts. Click the join button in any YouTube video to pledge your support.
Okay guys, so let's just jump right into it. I guess my first question is about just the overall robot footprint and packaging of everything. You guys have built very, very different robots throughout the seasons. I mean, I remember your Freight Frenzy robot, and then last year with Center Stage, and then now your last year with Power Play, and now your Center Stage robot. I feel like this one is much smaller than the previous ones. I could be wrong, but I think that's how it seems at least. So why don't you walk us through like the footprint and then the overall packaging going on, on the underside of the robot.
Sure. So our robot is 14 inches by 12 inches. And I guess talking about the packaging, we really wanted to keep everything very modular. So if you look at the inner side plates, all of our subsystems kind of attach onto these inner side plates here, which allows us to be very modular. And then speaking about the packaging on the drivetrain, we have a pretty standard parallel plate four-wheel mechanism, and we have 435 RPM motors that drive our mechanism wheels.
Mm-hmm. Yeah, and so while we're already down here and we have this fantastic shot of the bottom, it looks like I see at least 7 motors down here. So are you guys just using 7 motors on your robot, or do you have like an 8th motor somewhere else?
Yeah, we currently just have 7 motors down here, and we all have them pretty low, as you can see.
Mm-hmm. And so just as far as like the distribution goes, is that 4 for the drivetrain, 1 intake, 2 lift, and then hang is off of servos or something, or how does that work?
Yeah, that's right.
Okay, I see. And as far as materials go for everything, is it just like fairly standard 1/8 inch aluminum, or do you have something else going on there?
Yeah, so we actually have 1/8 Delrin on the inside here, and actually the majority of our plates are cut out of Delrin. Just the outer side plates we use 1/8 aluminum, and we're able to do that later on in the season.
I see. Yeah, no, that makes a ton of sense. And so now talking about a little bit about localization and sensing, your guys' autonomous consistency is really just unparalleled, I would say, so far into the season. I mean, every single match, 2+2, 2+4, when it mattered, you guys had it. So what sensors do you guys have for autonomous, and just walk us through that briefly.
Right. So for our sensors for autonomous, we have over 22 sensors on our robot. Some of the most important ones are the 3-wheel odometry that you saw on the bottom. We also have 2 corner ultrasonics here for detecting our partner. We also have a front ultrasonic that's kind of hidden right here. I think one of the most unique sensors that we have on our robot this year is our front-facing AI camera. It's a Husky lens, and it's able to detect the stack, and that enables us to improve our consistency with lining up with the stack. In addition, we also have a rear-facing camera right here that's also for detecting the APO tags, and we fuse both the ultrasonic data and our APO tag data, as well as our odometry data, in order to have a really accurate estimation of our robot's position on the field.
Wow, yeah, no, that is super interesting. And so, talking a little bit about those ultrasonics, I feel like I haven't seen a lot of teams mount them at 45-degree angles. Can you talk a little bit about what went into the decision behind that and how that's resulted, the results you've seen with that?
Right, so the 45-degree angle was so that we wouldn't need to necessarily turn the entire robot's chassis to see our partner if they're already at the board, and so that we can avoid colliding with them.
Mm-hmm. Yeah, no, that makes complete sense. So now going on to your intake, you already mentioned like the AI Husky camera that you guys are using for that. But now talking just a little bit about the hardware, can you give us an overview of the design and then we'll jump into more specifics?
Yeah, sure. So the intake is 3 stages of tubing. So we have one of them is a drop down, so we can use them on the stacks. And then we can also use them in teleop, so we can drop them down and intake from corners, for example.
Mm-hmm.
And one of the most unique thing is entire intake is powered by just one motor, including even the bottom roller is powered by the same motor. So how we do this is all the top 3 stages are connected by belts, and the bottom one is connected by actually 4 gears in a chain. So it reverses the direction of the spin of the motor.
Mm-hmm.
So we're able to intake efficiently with just one motor without using any additional servos.
Yeah, that makes complete sense. And so now talking a little bit about the progression of your intake, I mean, there's a lot of different components going on there. You said the bottom roller, the first stage, the drop down and everything. Have all of these been here the entire season, or were there like some iterations that you made that you think were really key to the success of your intake?
Yeah, so one of the biggest problems we encountered during the season was pixels going in vertically and jamming the entire intake. So the way we prevented that is actually with this front piece over here that guides the pixel down. Mm-hmm. So in auto, the pixel will be up here, and then this piece right here will guide it down to be all the way at the bottom. And this pretty much eliminated all vertical jams. And another thing we did is on the first stage over here, adding onto the tubing that we have, we also have these kind of stationary wheels. Mm-hmm. So these also help to make sure that pixels don't go in vertically and to keep them flat. Another thing is we have a belt running between the first and second stage here, so that basically the pixel, like, it's pretty much impossible for it to go up vertically. The belt will always push it down.
Yeah, no, that makes a ton of sense. And while we're already here and we have this fantastic like up close shot of your intake, I feel like with a lot of teams, we'll just see just like surgical tubing everywhere. But with you guys, I feel like we see a different sort of actuator or like component interfacing with the pixels at every stage. I see like some sort of like paddles or gear looking wheels in the back, and then compliant wheels, and then like these 3D printed star shaped intake components in the front. So walk me through like the decision behind having so many different types of tubing and intake components.
Yeah, sure. So for the first roller over here, since we're using them for stacks primarily, we want to make sure the speed is as high as possible for these. So the gearing is geared down, and you can make this spin as fast as possible. And also these are TPU 3D printed. These are also really, really compliant. The walls are really, really thin, so we can be more flexible, and it won't disturb the stack as much when the intake. Onto the first fixed stage over here is again, it's still TPU. It's pretty similar to the design of the first roller, but they're thicker and they're longer. Having it thicker means it's more stiff, so you can intake them more efficiently and faster. And back onto the third stage, we initially started with surgical tubing for the third stage, but we realized that the surgical tubing actually resulted in a lot of inconsistencies for the transfer. Mm-hmm. So we switched to custom 3D printed TPU wheels at the back, so the pixel can go in at a very steady pace, so it doesn't disturb the transfer.
Yeah.
But we kept one of the tubings on this stage, so that like if the pixel going at a weird orientation, the tubing will hit it from the side and fix the orientation as it goes in.
Yeah, no, that makes sense. And so a couple questions there about the TPU, just because, some of our viewers may not be as familiar with it as compared to PLA or other more common 3D printing materials. What type of printer do you guys use for this? And like, would you recommend teams to print intake noodles out of TPU, or like, have you had any rigidity issues or anything like that, or like longevity issues?
Yeah, so to print the TPUs, actually primarily all the 3D printed parts on this robot is printed from a custom machine that I built over the summer. It's the Voron 2.4. It's a lot larger than any of the printers that are currently available, and it's also faster, more precise, and it's able to print, for example, like materials such as like ABS TPU, like really, really easily and really fast. Mm-hmm.
Yeah, that makes sense. And so you guys haven't had any issues with like your TPU stars breaking or anything like that, correct?
Yeah, we haven't had any breakage issues.
Makes sense.
Yeah.
Makes sense.
one thing we did to enhance the strength, on the inside of the TPU studs, we have a separate material.
Yeah, so these rollers, like the outside is TPU, but the core of the thing is ABS.
Okay.
So this is to prevent like the thing from slipping.
Mm-hmm.
So originally we started like the entire thing as one single TPU piece, but we found that like under a lot of torque, it can actually slip on the hex axle. So the inside is with ABS core.
Yeah, no, that makes a ton of sense. So now going more towards your transfer, I mean, you guys are obviously no strangers to using sensors throughout your robot. So as far as your transfer goes, do you have any sensors you need there, or is it just entirely mechanical?
Yeah, so one of the main issues that we had was not being able to detect the pixels after they go to our transfer place. Mm-hmm. So the way we solve this is through a color sensor. If you can send the slide. So if you can see down here, we have a color sensor. Essentially the way it works is we intake 2 pixels. So Neil, you want to demonstrate that? So 2 pixels will go in, and essentially when the pixels are stacked on top of each other, the color sensor inside here would be able to detect it. And something we're doing unique is that we're actually not using the color sensor mode on this red color sensor. We're using the proximity mode, which essentially tells us distance away. Mm-hmm. So if there's only 1 pixel, the second pixel, like the height, would not be high enough to trigger the proximity mode. It's only when there's a second pixel in the transfer, then it would know that there's something nearby, and we know we have 2 pixels stacked on top of one another.
I see. Yeah, no, that makes complete sense. And so now that you have your pixels in your transfer, how does your claw work from there? What actions are taken in order to grab the pixels and then go onto the deposit?
Sure. So essentially our pixels would come into our transfer location, and then our claw, as you can see, it has 2 separate prongs. Essentially the way this works is it's offset by roughly 10 degrees through this rubber band right here. So essentially the first claw, which is the bottommost claw, will be able to release first. So if we were to have 2 pixels inside here, they would be in the correct orientation. And essentially this one will release first just because it's offset by that 10 degrees that I mentioned. Uh-huh. So the first one will be able to fall out, but the second one will still be within our claw. And then if we open up our servo, which is actuating all of this, opening it up a little bit more, then the second pixel will fall out as well.
I see. And so it's one servo that actuates both claws, but you always drop one first, and then you can control when you drop the second. Is that correct?
Correct. So it's just one servo that's located right here. Mm-hmm. And since they're offsetted slightly, that means the first set of claw prongs will open up before the second set of claw prongs, so we can individually deposit them.
I see. And what servo are you using down there? I saw like a silver servo that I don't think I've seen before, and maybe a lot of our viewers haven't either. If you could go into that a little bit.
Yeah, sure. So that's a Pro Modeler. The reason for that is just that it's very high speed, and it also has a lot of torque. So these don't burn out that easily, although they are quite expensive.
Mm-hmm. I see. Okay, and now talking about your deposit, I see another thing that you have is kind of a tongue or lip. I'm sure you guys have another name for it, but coming out of your deposit, what exactly does that do? What's its functionality?
Sure. So one of our goals was to be able to remove pixels on the board, so relocate them or remove them completely. And the way we achieve that is through this prong, as we call it. The way this works is essentially we can either be in 2 modes. This will be the deposit mode, and then when the drivers want to go to the pixel reorientation mode, the claw would rotate such that it's facing like this. And then essentially what we do is we could grab the pixel either from this inner part or from the edge of the pixel and be able to move it around the board.
Mm-hmm. Yeah, no, that makes complete sense. And I mean, I know I was watching your guys' finals matches and qualifications, and it proved to be extremely effective throughout those. So, clearly a well-designed mechanism that's serving its purpose. Now, talking about the rest of your deposit, the arm itself, I see you guys have a lot of servos, lots of gears, and degrees of freedom. Why don't you walk us through what's going on there?
Yeah, sure. So essentially the way this works is the arm is along a carbon fiber rod. You can't really see it because it's enclosed in 3D printed clamps, but the carbon fiber rod is located at the center here. and then the 3D printed clamps are on that carbon fiber rod.
Mhm.
So we use helical gears, which means they self-align. So it minimizes the amount of drift in the gears themselves.
Mhm.
And then also on the two servos that actuate the arm, we also have these helical gears so that the pattern aligns.
Mhm.
So these are the two arms that control this joint right here. And then to add on to that, we have another joint which is controlled by this servo right here. This just allows us to be completely pass-through, meaning we'll pick up in this orientation, move the joint around, and then this servo will allow us to rotate to the opposite side.
Sure.
And then since this claw is, the outermost claw deposits first, this one will open first, and then the second inner claw will deposit second.
Mm-hmm. Yeah, of course. And so, now going on to your guys' end game a little bit, I think it's just so consistent. What, as far as the drone launcher goes, what actions do you think you've taken to make it as consistent as it is?
Okay, so basically the drone launcher sits on this MGN rail here, and an MGN rail allows the drone launcher to slide really easily back and forth, and this minimizes any inaccuracies that our launcher may have.
Mm-hmm.
And for the speed system, we have two sets of bungee cord on the left and right, and it's guided by this bearing over here and back to the bottom. So the reason why we did this is so that we can maximize the length of the bungee cord, so that the acceleration is more linear. Yeah, and then for the release down here, we have a servo on a latch. So when we release it, when we pull the servo back, it releases it and just flies forward.
Okay, yeah, no, that makes a ton of sense. And I mean, I think I saw you guys did like maybe hundreds of tests like the day before San Diego State's. Is that true?
Yeah, that's true. So before San Diego Championships, we did maybe 200 runs, and we recorded every single one of them on a spreadsheet. And the day before, the 2 days before the competition, we realized that the drone was illegal, so we had to switch the drone design. Because the previous drone design, the wings are actually folded together.
Mm-hmm.
And we read the rules and it says it's illegal, so we had to switch to this design, and the wings can go apart like these.
Mm-hmm.
So we had to do a ton of testing the day before to make sure the new drone design was well. And we did 103 tests too, and we recorded every single one of them.
Wow, yeah, no, that's really awesome. And as far as your hang is concerned, I see you guys have the winch system, but to raise it up, what is the mechanism behind that?
Yeah, so essentially our hang is composed of two main components. The first is our servos. These are Axon Max. These just have enough torque to lift the robot. And then on that Axon Max is a 3D printed spool with string. So the way this works is that there's a bungee that wants to pull the hanging mechanism down in this direction,
Mm-hmm.
but the string, which is on the spool, is pulling it in the opposite direction. So that means when we release this spool or rotate it in the counterclockwise direction, the hang will move upwards.
Mm-hmm. Yeah.
And all of this is on a Delrin arm, which is 1/8 inch Delrin with a 1/8 inch Delrin hook.
Yeah, that makes complete sense. And so, Clueless, I guess, looking forward to Houston, you have 6 or 7 weeks, I guess, maybe 5 or 6 weeks before you have to go compete in Houston. Clearly, this robot works extremely well. You have the world record, you have the #1 ranking in pretty much every statistic. Are you planning to make changes, pull up with a new robot, or do you think you'll keep this one and just make small improvements?
Yeah, so one of the main things that we wanted to do was just clean up our wiring, make sure that no wires can get pulled out. The way we're planning to do that is just recutting the outer side plates. We also wanted to make this less flimsy by just having 1/8 inch aluminum plate going along the length of the arm. Other than that, I think we want to just continue optimizing our autonomous, making sure it's reliable, and continue to do driver practice.
Yeah, no, that makes a ton of sense. So Clueless, thank you so much. I have been really excited to do this interview for pretty much the whole season, but especially after seeing your guys' performance at San Diego Regionals last week. Thank you so much for the interview. I think the community is really going to learn a lot from it. There's just so much going on with this robot, and I can't wait to see how you guys do at Houston. Reporting for First Updates Now, I'm Abbas, and this is Team 11212, the Clueless. Thank you.
This video on fun is brought to you by viewers like you and also in partnership with the following. Discover how Kettering University students engineered their success with Kettering's amazing co-op employment programs where students earn great pay and gain valuable experience. Those accepted into Kettering University can apply for a robotics scholarship, providing up to an additional $5,000 a year in tuition assistance. Head on over to kettering.edu/first to learn more and apply.